We're now at the main body of the pamphlet, which will be in 4 sections. But before I start, I want to give this a subtitle that may sound pretentious, the Reflections on the Motive Power of Agonists, but many of you will know that this is an homage to Sadi Carnot, who wrote what is perhaps the most important scientific document in history, which is called Reflections on the Motive Power of Fire, self-published in 1824, and is considered so important because it applies to absolutely all natural sciences, from cosmology to quantum mechanics. And it's because the motive power of fire is the foundation of the field of thermodynamics. So we're going to be talking about agonist energy efficiency. When I say energy, I mean free energy. I'm just going to say energy, though. And also, when free energy is proportional to the logarithm of an equilibrium constant. So anytime you see a log equilibrium constant in the rest of this talk, that's just another way of saying energy. We're going to be taking ratios of energies so that the scalar that turns this into a number, a free energy number, is irrelevant. It'll cancel out. So just the log of the equilibrium constant is what we're going to be talking about. So these are the 4 sections of the body of the pamphlet. I've designed these to be listened to independently. So feel free to stop and start as you go through this pamphlet because it's quite long. So let's start with some definitions of agonist efficiency. So we're going to start with an energy landscape, which is a potential energy surface shown here for an unliganded receptor going from between the C and O states. These energy wells are the points of stability, or the 2 stable states, and an energy landscape is a plot of energy versus structure. And you can see this would be the preparation that we're going to use for this, that applies to these landscapes and throughout the talk, unless stated otherwise. So in the absence of agonist, O is much less stable than C, so the probability of being open is quite small. It's an uphill reaction. But this situation changes when agonists occupy the 2 neurotransmitter binding sites. Agonists stabilize the C state to a certain extent, but because of strong binding, the higher affinity, they stabilize the O state to a much larger extent. And that turns this uphill reaction into a downhill reaction, and this low open probability into an open probability close to 1. And indeed, if we put numbers on these arrows, this is 8 kcals uphill, 8 kcals per mole uphill, minus 2 kcals per mole downhill. That's a 10 kcal per mole difference without versus with agonists, and that is exactly equal to the difference in binding between to O and C. This is 10 kcals per mole on the energy axis, so it's balanced. There's another state in here that we will consider later on, and that's this barrier region. It is a point of instability, and somewhere in this region is a point called the committer, or also called the transition state, signified by this double dagger symbol. And at that point in the reaction, the agonist has high affinity, and it is stabilized almost to the same extent as is the open state. Now that's important physiologically because it means that this difference in open probability is caused almost exclusively by an increase in the opening rate constants. You can see that the mountain gets much smaller when agonists are bound, and that's because it's binding with high affinity to that transition state. So that means when you put on an agonist, you get a rapid opening, or if you're talking about a synaptic current, you get a synaptic impulse. And the reason that happens is because the affinity change takes place before the transition state is reached. We'll go through this in the last section. So that means that going from C to O, you change your affinity before you hit that transition state, which means you get this lowering of the mountaintop. If that were not the case, If the affinity change occurred after the transition state, you would just get a small dribbling of currents. It would increase the open probability, but it would take place over a period of about 10 minutes instead of 100 microseconds. But let's not worry about that right now. Let's focus in on what counts for efficiency. We need to understand the sentence that agonists turn on receptors because they bind more strongly to the on conformation. It's this. If you understand that, you understand about 90% about what I want to say today. And in order to in order to understand efficiency, you need to understand just these two blue lines. This is the weak binding to C and strong binding to O. That's all you need to know in order to understand agonist efficiency. So that's what we're going to focus on. So if you take these four states and four arrows and stretch them out until they're flat, and you get a standard binding gating reaction scheme. So where the vertical lines represent gating, which is the global conformational change from C to O, and the horizontal lines represent ligand binding to the C and O transmitter binding sites. So receptors do more than just bind and gate. They enter desensitized states. They can enter complicated modal switches in behavior. They give rise to long openings and things we don't understand. And all of these things could be modeled by adding extra dimensions to this scheme. And it's true that, let's say, desensitization does contribute to the cellular response. We're not interested in cellular responses here. We're not going to analyze them much. We're interested in just the binding and gating. So we get rid of these in the course of our experimentation. We do whatever we can to get rid of anything that is not binding and gating. So we don't have to worry about these events in our analysis, in our quantitation of what's going on. And indeed, this red line represents what happens in cells for the most part. These states at the bottom are hardly ever occupied, so you can ignore these. So in a normal dose response curve, all that counts is the progression through these states highlighted in the red line, and indeed it's often drawn as a straight line because you don't have to worry about the other states. And that red line represents the dose response curve. So muscle type acetylcholine receptors are heteropentamers, which means we can make a mutation or use a toxin that disables one of the two binding sites, leaving only one functional. And we can study that binding site in isolation. And when we do that, the reaction scheme is this simplified version shown to the left, where L represents the gating equilibrium constants and KD represents the equilibrium dissociation constants, either to C or to O. And I want to highlight that this zero means, the subscript means zero agonist, and this means one agonist. So zero, it doesn't mean zero current, it means zero agonist. So in a thermodynamic cycle without any external energy input, getting across the diagonal is the same regardless of the pathway. This is called Hess's law. It was an empirical observation by Germain Henri Hess way back in 1840. So that he noticed that the product of these two equilibrium constants, the clockwise equilibrium constant, should equal the product of the counterclockwise equilibrium constants without any external energy. And that leads to this equation here to the right, which is that the ratio of gating constants is equal to the ratio of binding constants. And that ratio was called the coupling constant, which I'll abbreviate CC. So in this paper listed below, we measured each of these four equilibrium constants in complete isolation of the others, and we're able to confirm that this equation, which I'll call the green equation, is correct for four different agonists at three different kinds of binding site. these two ratios were the same. So that indicates that there is no significant energy coming into the system. The system is in thermal equilibrium. It's a thermalized reaction. We also learned that the sites operate independently insofar as the sum of the energies from the two sites is equal to the energy that you get from a two-site receptor. And we also learned that the adult sites are approximately equivalent in terms of their binding and gating properties. The fetal site with the gamma subunit is different, but we're not going to use that in the following experiments. So we can stick with this green equation here. By the way, these citations at the bottom, if you add my name, Auerbach, and the word buffalo to your search engine, you'll get a unique hit for that paper. So single channel currents was what we used to measure those four equilibrium constants, but we want to make this a more general applicable. We think efficiency applies generally, and most receptors are not ligand-gated ion channels, and even those that are, many of those are not able to be analyzed at the single channel level. So we are, from now on, everything I say is going to come from a dose response curve. So in a dose response curve, or a CRC, there are three key parameters. There's the maximum response, there's the minimum response, and there's the midpoint called EC50, which is where the response is half, the concentration in which the response is half its maximal. And it turns out you can relate these three parameters to all four equilibrium constants using the green equation. And I won't go through these equations here, but you can get all the four equilibrium constants of the cycle from these equations shown at the right. This is for a receptor with two equivalent binding sites. Now, in most cases, minimum is too small to be measured directly from the dose response curve. You have to get tricky and use some indirect methods of getting the minimum. But it can be gotten, and I'm going to show you one later on that you can get the minimum and efficiency just from max and EC50. So you can use just these two equations, which only have max and EC50, to get these two equilibrium constants, and these two are sufficient to measure efficiency in a tricky way I'll show later on. So you just fit this to some empirical equation, or you can even stick a ruler down and get a reasonable estimate of the max and EC50, and that's all you need to measure efficiency. So let's do some dose response curves. These are dose response curves from adult type muscle nicotinic receptors, and we do know L0, that unliganded gating equilibrium constants. The advantage of measuring it is once you know it for all agonists. So it's worth taking time to measure it. But we measured this, and this is the number we get. And these are now the three dose response curves for these three ligands: the neurotransmitter acetylcholine, the frog toxin epibadidine, and this small little molecule tetramethyl ammonium. So we fit this to a Hill equation, and we get max and EC50. We know min in advance, so we can calculate everything. Here are the EC50s and maxes, and we end up calculating the weak binding to C and strong binding to O, which is in the respectively in the micromolar and the nanomolar range. And we can take the ratio of those two equilibrium dissociation constants to get the coupling constant. So these are the coupling constants, and the coupling constant is a measure of agonist efficacy. So the way this works is you take the unliganded gating constant, you multiply it by this twice, 6,000 squared, in order to get out the diliganded gating constant, and then you can calculate max from that. So instead of using maxes as our indicator of efficacy, it's much more quantitative to use the coupling constant as the indicator of efficacy. So now you can see quite clearly ACH has 3 times the efficacy of TMA and 4 times the efficacy of epibadidine. So it's a nice way to get efficacy from that. So affinity comes from these two KDs, efficacy comes from the coupling constant, and as you can see, affinity can be anything. It's from nanomolar to millimolar. There's no real pattern. Any agonist can have any affinity in that range, and It's similar with efficacy. So here's a list of efficacies that we measured for a series of compounds. This is about half of what we have measured. The ones in blue are the physiologically, the ligands that are present physiologically. Acetylcholine and its breakdown product choline and its oxidation product betaine, which is trimethylglycine. And you can see that the efficacy, these are the coupling constants, and the right column is the log scale, where I've actually multiplied it by RT, the gas constant, times the absolute temperature to give you the energy in kcals per mole. This is on a log scale, where each unit change is 5.4 times greater than the previous, with negative being greater than greater numbers. So you can try to analyze this for structure-activity relationships. So here's a logical, rational series of ligands where we extend the methylene tail, and you can see as you start to extend it, efficacy goes down, but then it recovers. And the same thing with choline, where you move the OH group further and further away from the quaternary mean, and at some point the efficacy recovers again. But we didn't learn too much from those experiments. The main point I want to make here is that, as with affinity, efficacy can be anything. It's spread all over the map from 5 to 500 to 5,000. It's just all over the place. So that's affinity and that's efficacy. So finally we get to efficiency. The efficiency of a machine is defined as the useful energy out, or work out, divided by the energy going into the machine. So in words, in receptors, this means the fraction of binding energy, that's the energy in, that is converted into gating work. So this is a chemical, mechanical energy conversion process. That's what receptors do for a living. And efficiency gives you the fraction of binding energy converted into gating energy. So what are these two? What are the numerator and denominator? By the way, eta, that's the Greek symbol is eta, which is the standard symbol for efficiency in physics and engineering. Well, we know that, let's start with the work out. That's called the coupling constant. We know the L1 over L0 gives you the gating constant above the baseline, and that's equal to this binding energy ratio, which if you take the log, as I said, energy is just minus the log of an equilibrium constant, you get this in the numerator. And in the denominator, what's the energy in? Well, the energy coming in is the maximum energy you can get from binding, which is the high affinity energy, which is log KDO. So if you take that ratio, you end up with this equation here. Efficiency is equal to 1 minus the weak to strong binding energy ratio. And this equation, which I'll call the pink equation, is of similar form to the limit of the Carnot limit of a steam engine cycle, so with temperature replacing binding energy. So this is not a surprising form for this equation. Later on, I'll derive it in a different way that maybe will make more sense to you if you think this is a little hand-waving, which it is, but I'll show you another way of getting there later. So basic efficiency is the work out or the work in, which is also now the efficacy, log efficacy over log high affinity. So it's the affinity efficacy ratio. So efficiency is the correlation between log efficacy and log affinity. So if you have an efficacy, if the ligand has an affinity and it has an efficacy, then it has a correlation, a log correlation. It has an efficiency. So I'm going to use these two equations extensively, this green equation, which has been proven experimentally, and this pink equation, which I just derived for you. So I can show this graphically, these agonist properties as energy. Affinity is the magnitude of these two blue lines, the short one being the weak affinity and the long one being the strong affinity. Efficacy is the difference between these two lines, that's shown here by this white bar. And efficiency is the ratio of these two, or actually 1 minus the ratio of these two. So we have these three agonist properties, which are universal, applied to everything, every receptor and every agonist, can be related to these two blue lines as the magnitudes, the difference, and the ratio between the two lines. And I'll just say you can, in order to measure these three agonist properties, you can measure these any way you can measure these two equilibrium dissociation constants, KDC and KDO. We've gotten there through single channel kinetics and dose response curve or concentration response curve analysis. But if you can get yourself a stable bucket of closed and open or low and high affinity binding sites, you can measure them in some binding assay, however you want to do that. And I'll show you later, you may be able to get these from structure from PDB files. I'll show an example of how you can do that. The only thing I want to measure here is that these energy landscapes are drawn as smooth lines, but in fact they're bumpy. There are little microstates all along the way here, some bigger than others. It's probably a very corrugated surface, but none of these really will affect the efficacy, affinity, and efficiency parameters. Those are determined only by the length of these blue lines, which are taken by the bottoms of these two wells. So if you have a little glitch along the way here, it does not really change the definition of efficacy. So let's go back to our dose response curve. These are the ones that I got you before, and I will say now that those came from single channel measurements. We measured single channel open probabilities to build up this dose response curve, and we did so because it was very effectively we could get rid of anything that was not part of that binding gating cycle, as I showed you earlier, that it was all desensitization and other extra cycle events were eliminated from this accounting to get a very accurate estimate of the dose response. So these are the three dose response curves, and we take those numbers that I showed you previously, and you run them through our pink equation, and we multiply it by 100 to get a percentage, and we get the efficiencies of acetylcholine being 50% efficient, epibadidine 42%, TMA 54%. So half of the binding energy of ACH is converted to energy for the conformational change of gating. Now you can see right away that epibadidine is less efficient than ACH. ACH has a much higher maximum than epibadidine, even though the input energy is about the same. So you could tell just by inspection that ACH is more efficient, but it's nice to be able to know exactly to put a number on it. And you probably could not tell that that TMA was more efficient than ACH. And later on, I'm going to document that this 4% difference between ACH and TMA is significant. Now, I said on the outset that I was going to show you some whole cell currents. So first I want to say that affinity, efficacy, and efficacy again emphasize that they are universal agonist attributes. I want to say this is not something that just applies to the ACH receptor or to a few agonists. Every agonist, if you can get a dose response curve, you can get an efficiency out of it as well. So let's look at, we also did this using an ion flux machine measuring whole cell current dose response curves. And you can see they're not exactly the same probably because of desensitization. This had an exchange time of about 400 milliseconds, and I don't think we were able to completely eliminate desensitization in these. And everything was normalized to this asterisk point, to the response at 300 micromolar. So every cell, every run with every concentration was normalized to the value that we had at 300 micromolar ACH in order to get these curves. And we see we get efficiencies, when we run these through our equations, we get efficiencies that are not dissimilar to those of efficiency. They're about 3 or 4% lower, 2 or 3% lower across the board, but the relative efficiencies of the three ligands it shows up in whole cell currents. So not only is efficiency a universal attribute, it is also one that applies to whole cell currents as well as single channels. So that's the end of the definition section of the pamphlet, and the next section is going to be about patterns.